So in this video, we're going to see an introduction to differential equations. We're going to start off talking about what is a differential equation exactly. Is there a definition we can look at? Where do they come from? And what's the goal? And then we're going to get into different types. We've got linear versus nonlinear. We can talk about the order of a differential equation. We can talk about whether it's an ordinary or a partial differential equation. Just some notation that we could see throughout the course. And then end with talking about what a solution is for a differential equation. So a lot of definitions in this section and just general ideas. So when we talk about the derivative dy dx of a function, y equals phi of x, that derivative in itself is another function, and we use the derivative notation to denote that it is a derivative. For example, suppose we have a function y equals e to the 0.1 x squared. So we're talking about an exponential function here. This is just an example. If we were to take the derivative of that function, we could use the chain rule to take that derivative. So remember back in Calc 1, we would let u be the exponent. So du would be 0.2x. We would do a substitution. So we have y equals e to the u. Then we would take the derivative. The derivative would be e to the u times du, and then we would back substitute to find that. So then our derivative is 0.2x times e to the 0.1 x squared. Now, we started with a function. This thing is differentiable everywhere. So it's differentiable on the interval from negative infinity to infinity, which is what they're talking about there. When we take the derivative, we do get another function. Notice this is in terms of x, because x is the independent variable. Now, what if we were to take this guy and do a substitution here? Wasn't this originally y? So then we could say y prime is equal to 0.2x times y. So we're doing that replacement to get this. Now, what if you gave this to a buddy, a friend in this class or in a different calc class, and you said, here, find y, and that's all you gave them? Well, that's kind of what we're doing here in differential equations. We are given some kind of differential equation, whether it's a first derivative, we call that first order, or second derivative, second order. And we're asking, what is that function that satisfies that differential equation? What is our phi of x? What is that function? What does it have to be? So that's the whole goal when we talk about differential equations. So let's look at the definition. An equation containing the derivatives of one or more unknown functions or dependent variables with respect to one or more independent variables is said to be a differential equation. Now, there are two types of differential equation. There are ordinary differential equations and partial differential equations. Ordinary is what we're going to focus with here. We're taking the derivative of y with respect to x, so we have one independent variable. There are entire classes built around partial differential equations. That was one of my favorite classes in graduate school, actually. If you get a chance to take it because it's fun. I enjoyed it. So when you talk about partial differential equations, you're talking now about partial derivatives. And that's something you're going to see if you take in Calc 3. You've already seen them. If you're taking Calc 3 this semester, that's something you will get to see about midway through the course. Chapter 13, I believe, is where that is. So just to give you an idea of what's going on there, we have a function that's written in terms of a couple of independent variables. I'm just going to use something in 3 dimensions here. So we have z is equal to 2xy plus y squared. When we take partial derivatives, notation does change a little bit. Notice this funny looking d is actually a Greek d. That lets you know you're talking about a partial derivative. Because we have two independent variables in this equation, we could take a derivative with respect to x, and then we could take a derivative with respect to y. So the way that works, if we take the derivative of z with respect to x, then that means x is the variable we're dealing with. All of the other variables are treated as constants. So if x is our variable, and now we're to take the derivative of 2 times x times y, y is treated as a constant, treated just like a number. So this derivative would just be 2 times y. The derivative of y squared, if I take the derivative with respect to x, would be 0. Now, if we go down to this one and we take the derivative of z with respect to y, notice we're going to get something different here. If I take the derivative of this, now y is my variable, x is treated as a constant, so that first term has a derivative of 2x. That second term, if we take the derivative, using that power rule, would be 2 times y. So in partial differential equations, you're given this and you're asked, what's the original function that produced that set of differential equations? But what we're going to focus on are those ordinary differential equations. So let's look at a few examples. In that first one, we have dy over dx plus 5y is equal to e to the x. This is an ordinary differential equation. Notice that we've got that first derivative here. Y is the dependent variable, x is the independent variable. Now we could also talk about the order of the differential equation. And what's the highest order of derivatives that we see? Well, here we only have a first derivative, so we would call this an order 1 differential equation. If we look at that second example here, this is an ordinary differential equation also. Notice there's only one independent variable there. We do have a second derivative, so we would say this is an order 2 differential equation. And then if we look at this third example, notice I have a derivative of x with respect to t and a derivative of y with respect to t. There's only one independent variable, so this is an order 1 ordinary differential equation. We can have two unknown functions that we're trying to find. And in fact, we're going to see something similar to that when we talk about systems of differential equations. Now, in part B, these are examples of partial differential equations. And the giveaway there really is that notation that lets you know that these are partials. This is a second partial of u with respect to x. This is a second partial of u with respect to y. This is a second partial of u with respect to x. And then a second partial of u with respect to t. And then the first partial of u with respect to t. Both of these would be called order 2. This would be an order 1 differential equation, but once again, these are partial differential equations. So like we said before, there are classes built around partial differential equations. We're not going to go there in this class. We're going to get that foundation needed for that by focusing on ordinary differential equations in this class. So let's talk a little bit about notation. We are used to Leibniz's notation for derivatives. So that's the dy over dx, the d squared y over dx squared, and so on. We use that interchangeably with the y prime. So dy over dx is the same thing as y prime. D squared y over dx squared is the same thing as y double prime, and so on. In Calc 3, when you talk about partial derivatives, you will see this subscript notation. That's another notation used for partial derivatives. So it's the derivative of function u with respect to x, derivative of function u with respect to y, and then these are second derivatives. This is a derivative with respect to x, and then we took the derivative again with respect to x. This is the derivative of u with respect to y, and then take the derivative again with respect to y. This last one's called a mixed partial because we took the derivative with respect to x, and then we took it again with respect to y. So these are reserved for partials. That's typically where you see that. And then that last notation is Newton's dot notation. So if we were to take a second derivative, notice that second derivative becomes s with two dots over it. So if we had a first derivative, let's say we had dy over dx, Newton's notation would call that y with a single dot over it. Single dot for first derivative, two dots for second derivative. The variable that's used is the dependent variable. You see this sometimes in physics books. We are not going to use that notation in this class, but just to let you know that if you do see it somewhere, that's what it's referring to as a derivative. So when we talk about ordinary differential equations, we want to classify by order and linearity. So the order, like we said before, is the order of the highest derivative. When we talk about an nth order ordinary differential equation, it's said to be linear if it's linear in y, y prime, y double prime, all the way up to that nth derivative. The format for an ordinary differential equation can be written this way. I like to call this standard form. And when you're talking about whether or not something is linear, there's a couple of characteristics you're looking for. First, the dependent variable y and all of its derivatives are of the first degree, which means that we haven't raised anything to a power. If you take a derivative and you raise it to a power, second power, third power, or whatnot, then it is no longer linear. And then the second thing you're looking for are the coefficients. Now, we're used to talking about coefficients in terms of just numbers. Once you get to higher level math, coefficients aren't necessarily numbers. They could be functions also. So these things in front of that nth derivative, the n minus first derivative, in front of that first derivative and so on, those are actually called coefficients. So a naught is the coefficient of y, a sub 1 is the coefficient of y prime, and so on. We want those coefficients to depend at most on the independent variable x. So there's your criteria for is it linear? Do we have any derivative raised to a power? And then do those coefficients depend at most on x? Now keep in mind that also means that they could be constant. Because we could take any constant, I'll just call a constant c, and multiply by x to the 0. So it would be technically dependent on x, but we know x to the 0 would really be 1. So they could be numbers or they could be functions in terms of x. They cannot be functions in terms of the dependent variable y. If it's not linear, if one of these criteria has been broken, then that means that it is nonlinear. So when it's nonlinear, then we could have a derivative raised to a power, or one of those coefficients may be something like sine of y or e to the y prime. So let's look at a few examples. We want to determine in example 2, and then the examples after that, the order and the linearity of each one. So let's start with that first one. Notice that first one's not quite written in that standard form format we need. We want this to have all the derivatives on one side. Notice I've got dy over dx. I would have d squared y over dx squared, and so on. And then I have all my, so I have all my derivatives and my y term on the left. I have everything else on the right. So let's do some tweaking here. Let's tweak this guy by dividing everything by dx. Notice this one had separated the dy and the dx. So we're going to undo that. So when we do that, we have y minus x plus 4xy times dy over dx is equal to 0. So to put this in standard form, we're going to have that derivative piece first. So we have 4xy dy over dx. And then we're going to have plus y. So these two terms are staying on the left. This guy's going to end up moving to the right. Now we're asking, what's the order and is it linear or nonlinear? In this case, the order is 1. The highest derivative we see is that first derivative. But this guy is nonlinear. Can you identify the term that's the nonlinear term? What makes this nonlinear? Well, in this case, what makes this nonlinear is the coefficient 4xy. This coefficient is dependent on both x and y, and we need it dependent on just x. Now, the coefficient in front of the y is fine. That's a 1. This term over here is just in terms of x. So that's fine. But the whole issue is really just this first term right there. That's why it's nonlinear. Let's look at the next one. This guy's already written in standard form for us. We have all of our y stuff, our derivatives of y, and then y term on the left. Everything else is on the right. So let's look at those coefficients. We have a 1 in front of that y double prime. We have a negative 2 in front of the y. We have a 1 in front of the y here. We actually could combine like terms. That would be a good thing to do. So y double prime minus y is equal to 0. That's another way to write that. In this case, our order is 2. There's our second derivative. And this guy is going to be linear. The coefficients are 1 and negative 1. And our g of x, which is on the other side of the equals, is 0. So it's constant. Let's look at 3. So this guy's written in proper form. We have all the y stuff on the left. We have all the other stuff on the right. So our order here is 3 because we have that third derivative. Now let's examine those coefficients. That coefficient is just in terms of x. This one's just in terms of x. This one's a constant, so it's fine. And then our g of x is just in terms of x. So this guy's linear also. So this is where you may want to pause the video and see whether or not you can identify whether the order, or whether it's linear or nonlinear, and then the order of the differential equation, and then come back and check. So if we look at that next one, number 4, this is not quite in the form that we need. But we can already see there's going to be some issues here. We have y prime, we have this function. That's really what's throwing everything off. Let me mark that in red. Because this function is in terms of y prime. So we would say this is nonlinear. Oh, sorry, not in terms of y prime. The function in front of the y prime is 1 minus y. So it's not in terms of x, it's in terms of y. That's the issue. I'm going to retract my original statement and say that this is in proper form. We have y prime, we have y, and then we have e to the x. There's no way to manipulate to get rid of that y in front of that. So this is a nonlinear differential equation. It is an ordinary differential equation. And it is order 1 because we have that y prime there. If we look at that second one, we have d squared y over dx squared plus sine of y is equal to 0. This isn't quite in proper form, but we already see there's an issue. I would move this term to the other side so we have negative sine of y. Now we're in proper form. We have all the y stuff on the left. And then notice we don't have a y term. Let me point to what I'm talking about here. We don't have one of those terms. The coefficient would be understood to be 0 there. But that term that's on the other side of the equals now is an issue. That sine of y is an issue because that sign is written in terms of the dependent variable. So this is nonlinear. Because of that, that's the issue term. I always like to circle where the issues are, why it's not linear. But this is in order 2. And then if we look at this next one, number 6. This is a fourth order because we have a fourth derivative. But once again, we have an issue right here. We could think about this as y times y. And now that coefficient in front of that y is y, so that's a problem. This is our problem term. There's no way we could just get a y there without, and keep it in proper form, which is that form, that standard form that we were talking about earlier. So this guy's nonlinear. Okay, also got a few more. Number 2, this guy's nonlinear. The issue is this term. We have a derivative taken to a fourth power. Can't do that for it to be linear. Number 4, this is order 3, before I forget, because we have a third derivative there. If we look at number 4, the order is pretty easy, right? The order is 2 because that's the highest derivative that we have. But this is nonlinear. Can you identify the issue? What makes this nonlinear? Well, what's making this nonlinear is this cosine. It's in terms of the independent and the dependent variables. Our independent variable is r, our dependent variable is u in this case. And we can't have this in terms of independent and dependent. It has to be in terms of just the independent variable. Number 6, if we look at this, the order is 2. We have a second derivative in there. But this guy is going to be nonlinear. Because of this term. We are dividing by that independent variable squared there. So that's the issue. And then if we look at 8, 8 is using Newton's notation, the dot notation for derivatives. Here's the issue. We have a first derivative that's squared. So this is a nonlinear differential equation. The order is 2 because that's the highest derivative that we have, which is right there. So now let's talk about the solution of a differential equation. Any function phi defined on an interval I and possessing at least n derivatives that are continuous on I, which are substituted into an nth order ordinary differential equation, reduces the equation to an identity. Remember, an identity is something where you have the same thing on both sides. So, and that's said to be the solution of the equation on the interval. So all we do to check whether or not we have a solution, just like when you solve an algebraic equation, you plug it in. And when you plug it in, as long as you get an identity, which means you end up getting the same thing on both sides. Maybe it's x is equal to x or 1 is equal to 1. As long as you get the same thing on both sides, then you know that that's going to be a solution for the differential equation. So anytime we talk about the solution, we have to also think about the interval where that solution is a valid solution. So you can kind of think about it in sense as the domain of the solution. And that's what that next paragraph is talking about. The interval I that's in that definition above is called the interval of the definition, interval of existence, interval of validity. I like to call it the domain of the solution. So you have to think about not only is it a solution, but where is that solution valid? And sometimes it can be an open interval between 2 points, A and B. It could be a closed interval. It could be an infinite interval. Maybe it works from negative infinity to infinity. Just depends on really that original differential equation. And remember, when we talk about differential equations, we're asking the question, where is it differentiable? Well, some things are differentiable everywhere. Some things are not differentiable everywhere. So that domain for that differential equation kind of filters into that solution. And we'll talk about domain a little bit later in a more in depth in another section. So let's look at an example here. So we want to verify the indicated function is an explicit solution of the given first order differential equation. And then they're going to ask us a little bit about the domain. So let's look at this guy. This is the solution that they're saying. They want us to verify that. So to verify that, we're going to have to find a derivative and we're going to have to substitute everything we have into here. So I'm going to insert a page because I'm going to need more room. And I'm just going to rewrite some things. So we have y minus x times y prime equals y minus x plus 8. They're telling us the solution is y equals x plus 4 square root x plus 2. They're saying explicit because they have solved this equation for y. That's why it's called an explicit solution. So if we were to take a derivative, we're taking the derivative with respect to x. Derivative of x is 1. When I take the derivative of this piece, I have to think about that as a chain rule. So I'm going to keep 4. I bring the exponent down. I subtract 1 from the exponent. So now it's a negative 1/2. And then you have to take the derivative of the inside. And the derivative of the inside is 1. If you wanted to write the u substitution out, you could write the u substitution out. Once you do that a few times, though, you may get to the point where you don't have to write the u substitutions out. So there's our derivative. Y prime is equal to 1 plus 2 over square root x plus 2. So let's take this guy and let's plug it in here. So we have y minus x. Well, y was this function. So there's y minus x times y prime. We want to know, is that equal to? So I'm using equals with a question mark over it because we don't know yet. Y is x plus 4 square root x plus 2 minus x plus 8. So we want to know, do we get an identity? Are these sides going to be equal to each other? So let's do some fancy math here. Those x's are going to cancel out. We're going to be left with 4 times the square root of x plus 2 times 1 plus 2 over square root of x plus 2. We want to know, is that equal to what's over here? Well, those are going to cancel. So we have 4 square root x plus 2 plus 8. So let's distribute that term. So we're going to have 4 square root x plus 2. And when I distribute the 4 square root x plus 2 to 2 over x square root x plus 2, notice those square roots cancel, so we're left with just 8. And that right-hand side does look the same. So we're going to say, yes, we have verified. So now let's talk domain. I like to think about domain as the place where this is defined for not only the differential equation, but for the solution. Now we know that this solution, I'm going to go back up here, has some issues, right? Because of that square root. We know that this guy has to be greater than or equal to 0. So x has to be greater than or equal to negative 2. So this solution has to also be in the domain of the original problem. And we really need to think about what this problem looks like in terms of the standard form. So I'm now taking this differential equation and we're going to tweak it. If we were to try to get this in standard form, so remember, standard form has y on one side, right? All the y stuff. This would be negative x plus 8 or 8 minus x. And if we were to try to make this a 1, so we have a 1 in front of that, y prime. The only domain issue we're going to have here is where y minus x is equal to 0 or where y is equal to x. Now we're asking, is this solution, x has to be greater than or equal to negative 2, okay? Well, it does fit inside of this domain. So we're going to say that that's our domain for this guy. As long as x is greater than or equal to negative 2, we're not going to have any kind of problems because that fits inside of there. Like I said, we're going to do more with domain as we go throughout the course. This is just a really, really broad introduction about that, about domain. Let's go to example 3. We're verifying another solution. We have in part A, dy over dx is equal to x, y to the 1/2, and they're giving us this, y equals 1/16 x to the 4th. They're asking us to verify that solution. So once again, to verify, you have to take a derivative. Now we need a first derivative here. So let's take that derivative. In part A, that first derivative is going to be 4 over 16, which is 1/4 x cubed. We're going to make our substitution. So our first derivative, 1/4 x cubed, is equal to x times y, which is 1 over 16 x to the 4th, to the 1/2. We want to know, are these sides equal? So that's why I'm using the equals over, the question mark over the equals, because we don't know that yet. If I take 1/16 x to the 4th to the 1/2, I'm going to get 1/4 x squared. And we can see that 1/4 x cubed will be equal to 1/4 x cubed. So we have verified that solution. B is going to work the same way. I'm going to ask you to take a minute and pause the video and see if you can verify that one. So in this one, this is a second order differential equation. Notice we do have to have a second derivative. So our first derivative requires a product rule. So first derivative of the second plus second derivative of the first. So there's our first derivative, x e to the x plus e to the x. And then if we take the second derivative, again we have a product rule. First derivative of the second plus second derivative of the first. And then take the derivative of the second term. So y double prime is equal to x e to the x plus 2e to the x. So now if we make our substitution, we're going to have the second derivative minus 2 times y prime, which is the first derivative, plus y. We want to know, is that equal to 0? So let's do some fancy math and distribute. So if we look at our x e to the x terms, those are going to cancel. And if we were to look at our e to the x terms, they are going to cancel. This is an identity. We do get 0 equals 0. Now the equation in part B is called a homogeneous differential equation. Some authors, when they pronounce that, or mathematicians, they call it homogeneous. Some call it homogeneous. My teachers always called it homogeneous, so that's what I go with. But they both mean the same thing. It's just two different ways to pronounce it. Okay, it's homogeneous because we got all the y stuff on the left, so this is in proper form or standard form for a differential equation, and it's equal to 0. So one solution of this would be called the trivial solution, where y is equal to 0. So if y is equal to 0, then y prime is equal to 0, and y double prime is equal to 0, which means if we were to substitute that in for those, we would obviously get 0 is equal to 0. When we have a homogeneous differential equation, we're asking, is there a solution outside of the trivial solution? Because we already know the trivial solution will work. So that's kind of what we're looking for there. And there are techniques we can use to solve that. We'll see those later. I do believe that comes up in chapter 4. So good times coming up. When we talk about domain, I want to go back to that idea here so we can talk about it for these two. The domain has to work for the differential equation, and it has to work for the solution. So if we were to look at this guy, we have a y to the 1/2 power, which is the same thing as the square root of y. So notice this does have a restriction where y has to be greater than or equal to 0. And our solution here is y equals 1/16 x to the 4th. So there is a restriction on y. Y has to be greater than or equal to 0. But think about what's going on here. We have 1/16 x to the 4th as our y. So whatever goes in for x is always going to be a positive value because we are taking it to the 4th power. So even though there's that restriction on y, when I think about what's going on with this solution, because this guy's always going to be positive, and we always talk about domain in terms of x, what's going on with x. Well, x is always going to be positive, so there's no issues that are going to happen with that restriction on y. So I would say that the domain for this would be all real numbers. Any x value will work. B, if we were to talk about the domain, there's no restrictions over here. This guy's good everywhere. So the domain is going to be all real numbers once again. Oh, let's go back to implicit and explicit. When we talk about an explicit solution, we're talking about a solution that's written as y equals something. Implicit means that maybe you can't isolate y. So if you can't isolate y, then you write that implicitly. Think about things like an equation of a circle. If you were to look at that differential equation, it's not easy to solve for y, so we would usually write that as an implicit solution instead of an explicit solution. And example 5 is dealing with a circle. We have the relation x squared plus y squared is equal to 25. That is an implicit solution for this differential equation on the interval from -5 to 5. -5 to 5 because this is a circle centered at 0, 0, and it's has a radius of 5. So that solution set, if this is -5 and this is 5, would look like this. And we could go through and we could verify that this is a solution to that. So if we were to take the derivative here, this would be a derivative implicitly. So we would have 2x plus 2y prime is equal to 0. Solve for y prime. That's going to give us -x over y. So y prime is -x over y, and that is definitely equal to -x over y. So we get that identity once again. So let's talk about families of solutions. We know when we solve a differential equation, we usually get things written in terms of like a plus c. Think about Calc 1 when you were integrating something and you ended up with a plus c. You actually solved some really basic differential equations back in Calc 1 by using what's called separation of variables. Your instructor just may not have told you that. So if we had something like this, then we could integrate both sides. Really what you're doing is you're getting all the y stuff on one side and all the x stuff on the other side. And then you're integrating. And you always had that plus c on the end. That plus c gives you this family of curves that satisfies this system. That's what we're talking about here. There's a family of solutions. And unless we have a more details about what that solution looks like. Maybe we have a point, which we called an initial value back in Calc 1, and we will call it an initial value now. Then we can't really solve for C unless we know a point that graph has to go through. And if we do have that information, then we can plug in for X and Y, and then we can figure out what C is. But if you think about what this looks like, thinking way back to a pre-calc class, this is a family of quadratics. So it could be a quadratic that goes through 0, or it could be a quadratic that's shifted up. That plus C on the end is just shifting this graph up, or is shifting this graph down. So you're getting this whole family of curves where they all look alike. They are just positioned at different places along that y-axis. So when you're solving an nth order differential equation, so like if you had a second order differential equation, then what happens is you end up with two of those unknown constants. So you would need 2 points to figure out what those that constant 1 and constant 2 would be. If you have a third order differential equation, then you're going to have 3 of those constants. Fourth order, 4 constants, and so on. But either way you go, you're still thinking about this as a family of curves, a family of solutions that satisfies the differential equation. Unless you have enough information to find what's called that particular solution. And that's where those initial values come from, to figure out what that C is going to be. Later in the course, we're going to even talk about systems of ordinary differential equations, where we're going to have 2 or 3 equations, and we could do more, but we won't go past 3, I don't think. Unless, we won't have a whole lot of fun in the class, which would be amazing, right? So if we have a system of ordinary differential equations, then we're really coming up with, let's say we have 2 unknowns. Then we're coming up with 2 equations that will satisfy that system of differential equations. It's really similar to what you talked about when you're solving systems of linear equations. You were asking, what's the point that satisfies a system of linear equations? It had an x value and a y value. And that point had to work into that first equation and that second equation. Systems of differential equations are kind of the same way. We're asking what functions would satisfy both that first and that second differential equation. And so that solution, if we wanted to verify it, would have to work in both of those differential equations. So in this last problem, we want to verify the solution of the differential equation. This is a system of differential equations. And we could verify it just like we did before by taking derivatives and substituting in. So there's our system. If we were to look at the derivative of x with respect to t, derivative of the cosine is the negative sine. The derivative of the angle is 2. That is a chain rule. Derivative of the sine is cosine. Derivative of the angle is 2. And then if we were to take the second derivative of the sine is cosine. Derivative of the angle is 2. 2 times the negative 2 is a negative 4. Derivative of the cosine is negative sine. Derivative of the angle is 2. 2 times 2 is 4. Derivative of e to the t is just e to the t again. Then we need to take the derivative of y. Derivative of the cosine is a negative sine. So that's going to become a positive. Derivative of the angle is 2. Derivative of the sine is cosine. Derivative of the angle is 2. Second derivative. Derivative of the sine is cosine. Derivative of the cosine is negative sine. So now we have everything we can substitute in. I'm going to plug it into this guy first. So x double prime is equal to 4 times y. Here's my y. Plus e to the t. So if I distribute that's supposed to be a 2t there. Typo. And that's going to be a minus 4 over 5 e to the t, and then plus e to the t. So we're asking, do we have an identity? Change my color. We have the negative 4 cosine of 2t on both sides, the negative 4 sine of 2t on both sides, and if we were to combine like terms on the right, we will end up with the 1/5 e to the t. So we have verified the first one. And now we can do the same thing with the second. So into that second equation we go. We have 4 cosine of 2t plus 4 sine of 2t minus 1/5 e to the t as our y double prime. And that's going to be equal to 4 times x. X is cosine 2t plus sine of 2t plus 1/5 e to the t. And then we have a minus e to the t. Let's distribute the right-hand side. And once again, we're comparing. So we have 4 cosine of 2t on both sides, 4 sine of 2t on both sides, and we have a negative 1/5 e to the t on the left. If we were to combine like terms on the right, we will end up with a negative 1/5 e to the t. So we have verified that that is a solution. So we can verify solutions whether it's an ordinary differential equation or whether it's a system of ordinary differential equations. So we're going to do more with some of this in that next section.